Okay, so for this Electronics 110 lecture, we're going to be talking about ohmic devices. So this is our first lecture, so best to start with the basics. I'm linking two videos. One is going to be to the previous video, that's the syllabus video, just a little review as to what this lecture series is going to cover. And the other is going to be an introduction video. I'm going to try to link to an Electronics 101 video, which I feel is going to be helpful to understanding what we're going to be talking about in this lecture. So if you need a little refresher as to some of the topics, little insight as to the terminology, you watch the intro video for the lecture. This link's going to go to the first Electronics 101 video, which is the What is Electricity video. So again, some useful terminology. Going to be reiterating some of the things I said in that video, but watch it if you feel unsure as to what this video is going to be talking about. So, ohmic devices. What is it? The most simple ohmic device we can talk about is a resistor. An ohmic device is something that follows Ohm's law, which is V equals IR. I'm going to put a box around this equation because this is a very important equation. It is, without a doubt, probably the most important equation we're going to be using because we're going to use it everywhere. So just a little review. V is voltage measured in volts. I is current measured in amps. And R is resistance measured in ohms. So from this equation you can derive, or you can make several assumptions. For example, for a constant resistance, as voltage increases, current is going to also increase. That's a bad arrow. And as current increases, voltage across the device is going to increase. So that's for a constant resistance. You can also say a couple things about the resistance for a constant voltage. As resistance increases, current decreases, and then for a constant current, as resistance increases, voltage is going to increase. So these are a couple helpful relationships to know. Again, all of which can be derived from just looking at V equals IR. It's a simple line that you can draw with a positive slope. Generally, resistance is positive, meaning greater than 0. And we're going to treat that as such. There are very few cases where resistance can be negative, but we're not going to talk about them, so just don't worry about it. Resistance is a value greater than 0. Okay. So this is what an ohmic device is. This is what an ohmic device does. Generally, when you talk about something like a resistor, you say, oh, it reduces current. But in a couple scenarios, you're going to see you can use it to control the amount of voltage you get, and so on. So this is, again, what a resistor does. Now, the purpose of this first lecture is going to be talking about how to deal with resistors, because you can treat almost any component as having some resistance, as you'll see in later videos. But for now, what we're going to deal with is simplifying, I can spell, simplifying resistive networks, also known as the equivalent resistance method. So basically, what at the end of this, what you should be able to do is, if I give you, that's terribly drawn, if I give you a network of resistors, what you should be able to do is tell me what their combined resistance is. Meaning, if I were to take a resistance meter and stick one probe here and one probe here, what resistance would I see across the entire thing? Now, you use equivalent resistance generally just for resistors, but it can also be used, again, for later components. So if you have a bunch of very similar components in a very complex network, instead of doing some of the math you'll see later, you can just bring this all down to one component, and it's a lot simpler to solve. And simplicity is a good thing when it comes to electrical engineering, because it can get very complicated very, very quickly. So let's talk about how to simplify a network, and that's pretty much what this first lecture's homework is going to be. It's actually going to be 2 parts, but we'll talk about that a little bit later. So the most basic way to start looking at a resistive network is to look at the 2 configurations. Because the goal is to take the most sub network of it and then work outward, as you'll see when we work some problems. So there are 2. So there's the parallel configuration. Now, in parallel, you have a resistor on top of another resistor. So it's all in parallel. Or it's not in parallel. Wow. That's not parallel. That's series. I got ahead of myself. This is series, meaning one resistor is directly connected into another resistor. So we'll call this R1 and this R2. Remember, this can work for any number of resistors as long as they're stacked one on top of another. Now, the way to find the equivalent resistance of this, I can bring this down to one resistor, like so, and we'll call this resistor RT. RT is equal to R1 plus R2 all the way out to Rn. So for n number of resistors, this is the equivalent resistance. So the more resistors you add, it would make sense logically that the bigger the total resistance becomes. So that's a series connection. Current, this will allude to this for the next video. Current flows through all equally. So current at each of these is going to be the same. Voltage is different. Now, when I wrote V equals IR all the way back up here, what you can say is that the voltage across a resistor is equivalent to the current flowing through that resistor times its resistance. V equals IR. So as you increase the resistance, you get more voltage. Or as you increase current, you get more voltage. That's what this equation says. So you can look at either the current through the resistor or the voltage through the resistor if you know current or voltage. Vice versa. Again, this is sort of alluding to the next video. I'll reiterate this again in the next lecture. But it's good to establish it now. Get thinking about why current only flows in one direction, why it's equal through all of the resistors, and why voltage is different. So that's one configuration, the series configuration. Then there's the parallel configuration, which I got a little ahead of myself earlier. In a parallel configuration, all of the resistors are connected to the same wire, and I drew that a little too long. And again, this can be reduced down to one resistor, like so. So you've got R1, and then you've got R2, and then you've got RT. And RT, you can do this 2 ways. Flip over my notes. The simplest way to do this is 1 over RT equals 1 over R1 plus 1 over R2 plus ... 1 over Rn. So for n number of resistors, it's the reciprocal of the sum of reciprocals. That's one way to solve it. If you have only 2 resistors, it's also this. RT is R1, R2 over R1 plus R2. It's the product of sums, is what this is called. So there are two ways to go about this. You can derive this equation from this if you just do some clever shifting around, and you'll get these. Generally, this is going to be faster if you only have two, or you can start with two and work across for n number of resistors, or you could just do this. Either one works. I'm just giving you both options. Now, doing what I did for the series resistors or series elements, current is different through each resistor. Voltage is constant, so it's the opposite of series. And again, we'll talk more about this in the next video, but it's useful for you to start thinking about why this might be the case. Okay, so from this, by knowing series and parallel, you now know everything you need to start solving equivalent resistance problems, or basically taking a complex network of resistors and shrinking them down to just one. Okay, so let's start with a problem. And look at my notes, make sure everything's okay. So let's start with example number 1. So we're going to do like this, and then we're going to split here, one resistor, and then one resistor here. And I'm going to give these resistors values, and my math is going to be absolutely perfect and correct. So this is going to be 100 ohms, this is going to be 100 ohms, and this is going to be 200 ohms. Okay, how do you start? What you're going to do is you're going to look for the smallest set of network. So you're going to try and find the small set of series or the small set of parallel. So I'm going to circle and then reduce. So what I'm going to do is I'm going to start with these two, which are in series, instead of trying to deal with these two in parallel with this. Because what you want to do is have one in series with another, or one in parallel with another, not two in parallel with one, or one in series with two. You want to reduce it down so that you have one with one, because that's how this technique works. So I'm going to then draw this down here. So now we have one resistor in parallel with another resistor. Now I'm going to give these nodes names actually, so A, B, A, B. Okay, so let's solve for the equivalent resistance. We already know the resistance of this one because we wrote it down earlier. So these two are in series, so to solve them, RT is equal to R1 plus R2, which is 100 plus 100, which is 200 ohms. And I'll write this in blue so that you know that's what we solved. There we go. Okay, so now what? Now we've got one in parallel with another one, so what we can do is we can just take these two, say these are in parallel. Nope. There we go. And we can reduce this down again to one resistor. And so what is this? These two resistors are in parallel. So 1 over RT equals 1 over 200 plus 1 over 200, which is 2 over 200, which is just 1 over RT is 1 over 100, and we flip. RT is just 100 ohms. And there we go. So this is just a 100 ohm resistor. So we were able to take these three resistors, two in series to one in parallel, and reduce it down to just one resistor very, very simply. So let's look at another example. this one with a little more weight on resistors in parallel. So example 2, number 2. Thought I had another example. Doesn't look like it. Okay, so this will be the last example. So this one's going to take a little more effort to solve because it's going to be a little more complex. So you've got a resistor, another resistor, and then another resistor. Then 2 resistors here. And then just one more resistor here. Okay, so these 3 resistors are each going to be, not 400 ohms, 40 ohms. And these are going to be 60 ohms. And then this is going to be 120 ohms. Okay, so come on, mouse. There we go. So where do we start? Pick either one of well, we can pick whatever. But remember, you want to try and get it one in parallel with another, not 3 in series and with 2 in series in parallel with 1. You want to reduce it down to 1. So I guess we could start with this one. And then we'll just reduce that down to this. That was a crap resistor. That's a little better. So that gets reduced down to 1. We still have 1 and then 1. So we got 2 here and then 1 here. So let's solve this. These are in series, so it's very easy. We just add. RT is R1 plus R2 plus R3, which is 40 plus 40 plus 40, which is just 120 ohms. Underline that in blue so you know that's what we solved. 120 ohms. These 2 are 60 ohms. And this is 120 ohms. Okay, so we'll reduce these 2 now. That will again just be reduced down to 1 resistor. So we end up with something that looks like this. That as the video goes on, my resistors tend to look worse and worse. I apologize for that. Getting lazy. Okay, so we know that this is 120 ohms. This is 120 ohms. What's this one? Again, they're in series, so we just add. RT is R1 plus R2, which is 60 plus 60, which is just 120 ohms. And we will underline that in blue so you know it's what we solved. And now all 3 of these resistors are in parallel. So we'll just draw a big circle around that. And then we can reduce this down to 1 as we reach the bottom of the page. And so this is in parallel, so 1 over RT is 1 over 120, 1 over R1 plus 1 over R2 plus 1 over R3. Write down the equation first. I do that so that I always remember what equation I'm doing. Helps me better keep track of the variables. So 1 over 120 plus 1 over 120 plus 1 over 120, and I'll just skip the math here. And what are we left with? We are left with 40 ohms, and we'll underline that in blue. Yeah, that's blue. And that's 40 ohms. So there we are. We were able to take this very nasty looking network and reduce it down to just 1 resistor having an equivalent resistance of 40 ohms. So the end goal of this, like I said, is to try and reduce something very complex into something very simple. And that's going to help us solve current and voltage through each component equations in the next lecture. Which brings us to the homework. The homework is going to be it's meant to cover these two lectures. So it's going to have an equivalent resistance component, which is necessary to solve the problems, and it's going to have the actual solving the voltage and current through each resistor as part of the next lecture. Now, you can't do that part yet unless you already know it and you're watching this as a review. But what I do suggest to you is that you take the resistor networks and you do the equivalent resistance half first. And then when you learn how to do the solving the complex bits, then you can move on and you'll already have the first half done nice and easy, and you will have gotten practice. So that's what I suggest you do. I will post the homework in the description. There will be a link. I'm using Dropbox again. I actually have a dedicated Dropbox now, so everything should be lovely. But I think that is it for this lecture. Keep an eye out for the next one, and have a good day.